CAASTRO has three broad themes. We're looking at questions related to the dark universe, so dark matter and dark energy, what's their physical nature. There's the transient universe, so there's things that change in the universe on quite short timescales. And then the part of CAASTRO that my own personal research is in the evolving universe. And here we're looking at what a galaxy looks like and how it changes its appearance over these past billions of years of cosmic time that we can observe with these new telescopes.
The evolving theme in CAASTRO is actually the largest theme. It's the largest because it encompasses a large range of things, from galaxies to what we call the epoch of reionization. It covers a large range in cosmic time.
The epoch of reionization is a really crucial period. So in the very early universe we have the cosmic microwave background. We then have to go to the much closer universe, the much more evolved universe, where we see stars and galaxies. But there's a period in between there where we had to get from that microwave background, we had to build those first stars and galaxies. They had to transform the universe and the background of all that hydrogen gas in the universe to the universe we see today.
So we've spent a lot of time studying the epoch of reionization, or EOR, in CAASTRO.
When CAASTRO first began, we had a new low-frequency radio telescope, the Murchison Wide Field Array, but we were really just learning how to do this wide-field, low-frequency radio astronomy, and I think we've gone on to develop what's really a world-leading capability in that area.
The MWA has been enormously successful, so successful in fact that CAASTRO has helped lead an expansion of MWA, which is happening right now in Western Australia, and we've been able to help produce one of the largest radio maps of the southern sky at low frequencies that's ever been produced. Galaxies, of course, begin to form during this epoch of reionization, but they continue to evolve for billions of years after that. And understanding that evolution in CAASTRO has been very important for us, and we've been able to use some cutting-edge new instruments in order to do that. One is an instrument we call SAMI for short. SAMI has allowed CAASTRO astronomers to map over 2,000 galaxies so far, so it's really world-leading research that CAASTRO researchers have done.
SAMI is an interesting instrument. It allows us to get spectra at every point over the face of a galaxy in quite a lot of detail, and it allows us to do that for 13 galaxies at once. So for the first time ever, we're able to get what we think of as integral field spectroscopy, meaning spatially resolved images for each galaxy. So at each point on the face of a galaxy, we actually get a detailed spectrum which tells us a lot about the physics of the galaxy, how the galaxy is moving, what stars it's made of, what the elemental abundances are, and various other things. So we can learn a lot about the galaxy, and now we're able to do it not for the galaxy as a whole, with all the stars and gas and everything else all mushed up together, but in fact at each point separately on the galaxy. And that means that we learn a lot more about the internal structure, and therefore the history and the formation and assembly of that galaxy. One of the nice things about CAASTRO is that we're at a point in time where the data and the simulations are both becoming sufficiently detailed to have really interesting things to say about galaxy formation. With SAMI, we've got those 3D data cubes where we know how things are moving, how they form, what they're made of, and the simulations are able to provide us with equivalent things for theoretical mock universes, and so we can actually bang the two things together. We can confront the data with the simulations and learn something about both of them.
We've been revising all of the things which have been working perfectly for 40 years. Well, they have been working perfectly because we haven't gone as deep, as wide, as better as what we're doing now. And what we're seeing now is that 60% of the data we get is really good. This is something we didn't know 12 months ago. We didn't know how bad the data was and what the fraction was. We don't have to spend all of our time doing all the data. We can just take 60% of the data and just use our other time for more useful stuff.
We need to know how to compare different data sets, and I wrote what's called a cross-matching algorithm. So something that takes reported source positions and frequencies and fluxes and matches them from instrument to instrument. And in that way, we're able to subtract them from the images that we create to hopefully get to that signal detection.
We don't yet have perfect data, and we certainly don't yet have perfect models. But with the two together, we can use the data to say some of those models work and some don't, and we can use the models to say, that's what that data actually means. We can begin to understand what it is that's actually going on in our data.
The dynamic theme is split in halves. There's what we call the slow transients and fast transients. The slow transients are things that change, but change on timescales of days or weeks or years. The fast transients, on the other hand, change in terms of milliseconds.
One of the big advances of CAASTRO was the detection and the discovery of fast radio bursts by the Parkes Radio Telescope.
I think the coolest thing about the fast radio bursts is that you get to weigh the universe. There's a slight catch, and that is you've got to identify the host galaxy. That's where this field is now moving to. I think CAASTRO has helped establish that there is this population of fast radio bursts. Thousands a day occur in the sky. There's only ever been about 30 discovered, and CAASTRO has been involved in more than half of those.
The increase in the number of these fast bursts that we can detect and trying to localise them into galaxies, I think there's been enormous progress, and I think Australia really has a great position in terms of globally understanding these objects.
One of the impressive things about CAASTRO is a lot of these breakthroughs have actually been made by our PhD students. And one of the big breakthroughs was the discovery of plasma tubes in the ionosphere by an honours student, Cleo Loy. And that was particularly interesting because it was an entirely serendipitous discovery. So we set out to study distant radio galaxies and transient sources, but we were aware that the ionosphere, the Earth's ionosphere, was going to be a problem in detecting them. And so I gave Cleo the job of trying to quantify how much the ionosphere was going to affect our observations. And in the process of doing that, she discovered that you could actually use the MWA to study the ionosphere itself and noticed various phenomena. But then Cleo came with the sort of innovative idea of looking at this with respect to the Earth's geomagnetic field and realized that the phenomena we were seeing were aligned with the magnetic field, and so they were likely to be real. She then used the MWA as a sort of in stereo, as a pair of eyes, so that we could work out the distance to the objects. And that's something we would never think of doing, because usually the objects we're studying are too far away for parallax to be a useful measure. Doing this, we were able to confirm that they were in fact in the ionosphere, and that led to 5 publications and 1 million hits on YouTube, and a lot of interest from defence and from other scientists in both the ionospheric community and the radio astronomy community.
We have started detecting low-frequency flares from stars. So we expected to detect stars using the Murchison Wide Field Array, but when other scientists went and did large full sky surveys for transients, they didn't detect stars. And it was kind of a mystery as to why we don't detect these objects that we expected to detect frequently. My team actually determined that the sensitivities that we were looking at for the Murchison Wide Field Array were not actually sensitive enough to detect these flares. They're actually a lot dimmer than we first expected. And we found that we could actually detect these objects in polarization rather than total intensity. So we kind of found a new way to use the Murchison Wide Field Array to get better sensitivities and detect a lot dimmer objects. So that was kind of a key breakthrough to show that you can use the Murchison Wide Field Array in a more creative way, in a different way than normally how it's used, to actually find new things that maybe you didn't expect to detect given the sensitivities originally. With regards to the Murchison Wide Field Array, we've also had to come up with a lot of software implementation and try to reduce the data for the Murchison Wide Field Array, which means that now we have to use supercomputers, we have to use different programs that run on supercomputers to actually reduce the data, and this is a lot more data than an average radio astronomer is used to. So just coming up with methods and techniques to reduce the data, to use the data, has been a great advancement within the field.
The dark theme in CAASTRO is trying to understand dark matter and dark energy. We measure the positions of galaxies, the motion of galaxies, and exploding stars called supernovae to trace the expansion of the universe, and together they give us a great test of what the dark energy and dark matter could be.
CAASTRO has 3 experiments running to probe dark energy. There's the OSDES survey, the 6DF survey, and the WIGGLE-Z survey.
One of the great successes of CAASTRO was the survey called WIGGLES, where we measured the positions of almost 250,000 galaxies. And with that made what at the time was the largest map of the distribution of galaxies in the universe. What we're looking at is basically a massive pattern of sound waves in the imprint of the positions of galaxies. Those sound waves basically meant that we have sort of a ruler that you can use to measure the expansion of the universe and how that's changed over time. And that confirmed the discovery of dark energy.
When we try to infer the properties of dark energy, we compare the properties of nearby supernova and distant supernova. And you need a survey which finds the nearby supernova, which is SkyMapper, and you need a survey which finds the distant supernova, which is the Dark Energy Survey, which AusDES is a part of.
AusDES is the Australian Dark Energy Survey, and we're working with a big international team of observers in the Dark Energy Survey to measure thousands of supernovae and use those to trace the expansion history of the universe more precisely than ever has been done before.
A lot of Australia's involvement in DES has been enabled by CAASTRO. We're coming up to being able to release data from the first 3 years of DES, which is a massive effort, and that's going to be a really exciting time.
So SkyMapper has been working continuously since last year, so it's now that we're getting all these Type 1a supernova. So we have right now 35 Type 1a supernova confirmed from SkyMapper, and this has been the job from the SkyMapper Transient Group. Now, our goal is to get 150 Type 1a supernova at this volume, and I think we're in a good pace to have it in a couple of years.
Most of the mass in the universe is actually dark matter. It's not the galaxies that we can see. Galaxies fall towards dark matter clumps. So even though we can't see the dark matter itself, by watching what galaxies are falling towards, we can detect its existence. So using what we call peculiar velocities, the motion, we can infer how much dark matter is there and what its distribution is. With CAASTRO, we had a project called the 6-degree field galaxy survey, with which we measured the elliptical galaxies, looked at something called the fundamental plane, which gave us their distance. And using that and their spectrum to get their redshift, we could figure out their motion. We also had another project called the 2-mass Tully-Fisher survey, with which we measured spiral galaxies and measured their velocities. And together, they gave us a map of the motion of galaxies in the universe that we used to test theories of dark matter.
We've been very blessed in that the Dark Universe discoverer became the Vice-Chancellor of our most prestigious university. The evolving theme has evolved into Astro 3D, which is sort of a successor to CAASTRO, and OSGRAV is a natural consequence of the dynamic theme.
This won't disappear, this momentum within the community, the collaborations that we've built, these now exist, and the 7 years is long enough to really propel them forward.
People look to CAASTRO and see something that's been very successful, and they see that that's based not only on careful organisation and use of money to do particular research programs, but also to this broader base of changing the culture and the way that we do research. And I think that impact is the really long-term legacy of CAASTRO.